Good day, I'm J Wildberger. Today we're going to be talking about an extension of polynumber on sequences where we move to rational polynumber on sequences. And this will give us also an opportunity to introduce in a very gentle way the idea of a limit, rather informally and in a very simple example. We'll also be introducing some important new terminology, an extension of our number field to include infinity, which might be rather interesting. Before I get going with today's lecture, though, I would like to do something else, which I'm going to be doing a little bit more regularly as we go along. So as you know, I'm critiquing modern mathematics here. I'm questioning the foundations of analysis. My claim is that the modern foundations of analysis don't really work. And so I think it's useful to occasionally present you with some evidence of that from the literature. Today what I'm going to do is just very quickly have a look at a lovely book. So periodically I'm going to show you some books and we're going to talk about them, and especially with the relations with the foundational aspects. And I should say that all the books that I'm going to show you are books that I value highly. I'm not going to bring any books and show you them unless I already respect them and value them as important contributions. So even though I may be saying some negative things about the books I'm showing you, still overall I think quite highly of them. The book I'm showing you today, this one here, it's called Selected Papers on Calculus. It's already about 50 years old. It's by the Mathematical Association of America. And it's a very interesting compilation of many articles that have appeared over the years in the American Mathematical Monthly, which is one of the most prestigious and mostly wide-read of all popular mathematics journals. And all these articles have to do with calculus in one way or the other. And there's probably about 150 different articles, very nice ones, a lot of interesting material here. And what I want to point out to you is that scanning the articles here, which range from the history of calculus, pedagogy, talking about functions, continuity, differentiation, derivatives, polynomials, integration, of course, techniques of integration, summation, sequences, special numbers like pi and e. Despite the many articles that are found in this book, very few of them actually deal with foundational questions. The pure foundational questions of how does one set up analysis. So the critical issues of how we define what a function is, what are the definitions of the trigonometric functions, of the exponential function, of the log function, what are the definitions of the various constants like pi and e. More generally, how does one set up the real numbers to begin with? This all-important issue. These foundational problems and others, having to do with the nature of the derivative and the definition of the integral, a very important concept, are basically all finessed in this book as it is in many other treatments. There's simply this blanket assumption that all those issues are more or less bedded down and not even worth raising and examining. So it's like a survey of building or construction which doesn't have any chapters on how to lay the foundations of a house. There's something askew here, especially considering the very significant foundational problems that beset modern analysis in the early part of the last century. There was a lot of debate 100 years ago about how to set up analysis, about what continuity meant and what integration meant and various other things. In particular, the real numbers, how does one set them up? These questions have all now been largely relegated to ancient history, and there's a very convenient assumption by the Academy to pretend that all such problems are non-existent. There's a big elephant sitting in the corner of the room, and as long as we don't pay any attention to it, and it doesn't pay any attention to us, everything will be fine. So in subsequent videos, I'm going to show you some other textbooks, and we're going to have a look more and more as to how does modern mathematics actually address these issues that I'm talking about in this series. Okay, so today we're going to talk about rational polynumber on sequences, or maybe rational poly on sequences for short. And I'm going to follow a, by now, hopefully familiar framework. We started off with this course talking about natural numbers, integers, fractions, and working our way to rational numbers. Natural numbers like this. Integers were defined in terms of pairs of natural numbers. So 2 less 3. That was the way we introduced what we now call -1. We talked about fractions, 1 over 7, also built from natural numbers. And then sort of putting these two things together, integers over integers, making rational numbers, and they are the sort of prime objects for doing arithmetic in everyday life. Rational number field. And then later, when we started introducing algebra, we went up a level of sophistication, started talking about polynomials, or as we preferred, polynumbers. And so analogous to this, we had a sort of a compatible structure of natural number polynumbers, or natural polynumbers, integral polynumbers, fractional polynumbers, rational polynumbers. Here's a typical natural polynumber. And then taking differences of them yields integral polynumbers. That's one way of introducing integral polynumbers. Another way is just to consider polynumbers with integer coefficients. Amounts to roughly the same thing. We can take ratios of them to create sort of fractional polynumbers. And if we do that with integer polynumbers, then we get the field of rational polynumbers, which is second in importance in mathematics only to the field of rational numbers. So rational numbers, rational polynumbers, these are fields that support our 4 fundamental operations: addition, subtraction, multiplication, and division. With just a little bit of a problem, we're not allowed to divide by 0. Otherwise, there's a kind of a uniformity and a completeness in these kinds of arithmetic domains. Okay, so having understood this framework, we're going to now go up a level to considering sequences or on sequences built up from the basic similar framework. So we're mostly interested today in these rational polynumbers and extending them to on sequences. So let's have a reminder of what these objects are like and how we do arithmetic with rational polynumbers. Now in modern mathematics, these objects are often called rational functions, which is unfortunate terminology. The rational polynumbers or rational polynomials is, I think, a superior notation, more properly captures what we're doing. So I remind you that rational polynumber is a formal ratio of two integral polynumbers. And there was an important notion of equality, that P over Q equals R over S, precisely when P times S equals R times Q. These 4 are all integral polynumbers. So you can think of them as polynomials with coefficients which are integers. Polynomials in alpha. So for example, here is a rational polynumber, and we'll write the over not with a slant like this, but rather with a horizontal bar because it's just easier to write. So this one here, 1 minus alpha over 2 plus alpha squared, that's the same as alpha minus alpha squared over 2 alpha plus alpha cubed. And why is that? It's because if you multiply 1 minus alpha times this, it's the same as what you get when you multiply this times alpha minus alpha squared. And we can see that in another way by just realizing that to go from here to here, we've multiplied the top and the bottom by the same polynumber, namely alpha. So to go from here to here, we've multiplied by alpha. To go from here to here, we've multiplied by alpha. That has the effect of making sure that this kind of equality is maintained. So these two rational polynumbers, they may look different, but they are actually officially exactly the same objects for us. It's going to be a basic but important point in today's lecture. Okay, and we can do arithmetic with these things. So for example, if we want to add this rational polynumber and this one, well then what we do is we take this times this plus this times this all over this times this. Just exactly the same way we add fractions. Of course, the simplification here is necessary to get it in standard form, top and bottom. So of course, arithmetic with fractions, with ordinary rational numbers, is a necessary preliminary to doing algebra with these rational polynumbers. And we can multiply two of them, in which case we just multiply the numerators and multiply the denominators. And we can also divide one by the other, which amounts to multiplying this one by the reciprocal of this one, what you get when you interchange the numerator and denominator. So I hope we're all comfortable with the arithmetic or the algebra of rational polynumbers. And let's just make sure that we're all on the same level here, that we all appreciate that these rational polynumbers are not functions. Okay? So they are not functions, first of all, because we have not got a comprehensive definition of what a function is. That's actually a very problematic issue. So for example, when we write down something like this, t equals 4 minus alpha plus alpha to the fifth over 5 plus 7 alpha squared, that is not a function. It is simply an expression that we write down in terms of alphas. So the expression itself lives above any particular interpretation of it. So someone can come along and say, oh, well, that looks like a function from the rational numbers to the rational numbers. And someone else can come along and say, oh, no, that looks like a sequence. We input a natural number and get out a rational number. Someone else might say, well, no, that's a function from the complex numbers to the complex numbers. There might be lots of other possible interpretations of this. But for us, the object itself is just the expression. We do not need to specify a particular interpretation of the expression. Okay, so earlier in this series, I gave an entire lecture on this issue of the difference between object-oriented mathematics and expression-oriented mathematics. And you will know that I encourage an expression-oriented approach to mathematical work. Okay, there's another important notion that we need to consider. That's the evaluation of rational polynumbers. So for example, if we stick with this one here, there's t, it's a rational polynumber. What is t of 1? Well, t of 1 is what you get when you replace the alpha with the number 1. So 4 minus 1 plus 1 to the fifth is 1, over 5 plus 7 times 1 squared, for a total of 4 over 12, which is a rational number, also equal to 1/3. Another example, we could also plug in an integer, say minus 2. Put alpha equal to minus 2, we get 4 plus 2 plus minus 2 to the fifth, which is minus 32. Divided by 5 plus 7 times 4, 28, giving us minus 26 over 33. So in general, the rule is that if we have a rational polynumber, which is a over b, where a and b are integral polynumbers, and if, say, k is an integer, then p of k is, by definition, the rational number a of k divided by b of k. So we have a well-defined notion of what it means to evaluate a polynumber at an integer, and we're evaluating two polynumbers and taking the corresponding rational number we get. So we can evaluate rational polynumbers at, say, integers. So now that we're all happy with rational polynumbers, let's use them to extend our notion of on sequences, to consider more general infinite sequences, And we're replacing the term infinite sequences with on sequences, short for ongoing sequences. So the idea is we're going to start with a rational polynumber, and we're going to generate a sequence from it. We'll call that a rational poly-on sequence. And here's our notation. It's already familiar by now, I hope. Left square bracket, the actual rational polynumber, and then a right pointed bracket. An alternate notation is we're going to replace the alpha in P with the letter n. N is our favorite number for sequences. And that expression will also indicate to us that we have a sequence here. And the crucial thing about a sequence or an on sequence is that we can pick out the kth element, where k is usually a natural number for us. So 1, 2, 3, 4, and so on. And the definition is that if we take this rational polynumber p and then generate this on sequence, then the kth element in that on sequence is by definition p of k. Now that's in general a rational number, not an integer. So k is an integer, but what's on this side here will typically be a rational number. So let us look at an example. Here is a rational polynumber p. It is 1 plus alpha minus alpha squared over 2 plus alpha cubed. So one integral polynumber in the numerator, another integral polynumber in the denominator. Then what is the corresponding on sequence, which we can write as the sequence p, or to be more explicit, we can write it this way with this expression put in here, the alphas replaced with n's. So the sequence 1 plus n minus n squared over 2 plus n cubed. Okay, and what is this sequence? It's the sequence that you get by starting to calculate the values of this thing, first when n is equal to 1, then when n is equal to 2, then when n is equal to 3, and so on. So for example, when n is equal to 1, we get 1 plus 1 minus 1 squared, that's a total of 1 in the top, divided by 2 plus 1, that's 1/3. And if n was equal to 2, we would have 1 plus 2 minus 4, that's minus 1 altogether, over 2 plus 2 cubed, which is 2 plus 8, isn't it? So that should be a 10, sorry. Minus 1 over 10 is the next one. And the next one, let's just check that. If n is equal to 3, 1 plus 3 minus 9, that's 4 minus 9, that's minus 5, over 2 plus 3 cubed, that's 2 plus 27, that is in fact 29. Alright, so if our arithmetic is good, we can carry on generating more and more terms. And of course the thing doesn't necessarily stop, it sort of keeps on going, depending on how much patience and computing power we have. We can keep on generating more and more terms in this ongoing sequence. So now we've extended our notion of infinite sequences or on sequences in an important way. We've gone from constant on sequences to polynumber on sequences and now to rational polynumber on sequences. So these are now much more general kinds of on sequences, and they're very important for us in calculus, as we'll see. So these are very much sort of workhorses of calculus. So it all seems very good. But, in fact, there is a big logical problem. So what I've told you in the last few slides is logically weak. There is a key problem that I have sloughed over and not mentioned. And I wonder how many of you have cottoned on to what that is. So it's now a great exercise to go over these few pages and to look very carefully at what I've done and ask yourself, okay, what is the problem here? There's a logical problem. So you might want to stop the video and go over these issues, have a look, spend perhaps some days thinking about it. Okay, there's a logical problem and you want to find out what it is. It's not particularly subtle. It's pretty straightforward, and once you see it, it's kind of obvious. All right? So please have a look, have a think about what is the logical problem that I've been ignoring here. So I hope you found what that logical problem is yourselves. Okay? And it comes down to a very common source of difficulty in mathematics, elementary but common, which is that division by zero is illegal. That's the one operation with rational numbers that we are not allowed to do. And unfortunately, we have built in the possibility of division by zero so far in our treatment of these rational polynumber on sequences. For example, suppose that we had looked at the rational polynumber alpha over 2 minus alpha. This is a rational polynumber because it's an integral polynumber over another integral polynumber. Okay, here's the associated rational poly on sequence, n over 2 minus n. What's the sequence associated to it? Well, we just start generating values. When n is 1, we get 1 over 2 minus 1, that's 1 over 1. When n is 2, we get 2 over 2 minus 2. That, unfortunately, is 2 over 0. When n is 3, we get 3 over 2 minus 3. That's 3 over minus 1. My arithmetic's not very good today. There we go. And we could keep on going, and there would be no more problems. However, there's no escaping the fact that when n is equal to 2, we have forced ourselves to make an illegal operation. 2 over 0, all bets are off. This object collapses as a logically coherent thing. It just does not work. Let's look at another example, slightly more complicated. Here we have a rational polynumber q. 1 over 3 minus 4 alpha minus 2 alpha squared plus alpha cubed. All right, so we can generate values. When you plug in alpha equals 1, then you get 3 minus 4 minus 2 plus 1. That's 4 minus 6, that'd be minus 2, so we get minus a half. When n is 2, hopefully it'll be minus 1/5. And what happens when n is equal to 3? Well, it's not so obvious here, but let's have a look. 3 minus 12, and then this will be minus 18, plus 27. So altogether 3 plus 27, that's 30. And minus 12 minus 18, that's minus 30. We're going to get 0 in the denominator. Again, this just does not work. This is not a legitimate object. So that's certainly a problem. But there's another kind of problem also. A more subtle kind of problem, but just as important. Consider the following example, which seems to be quite okay. The example r equals alpha over 1 plus alpha, the associated on sequence n over 1 plus n. This is clearly unproblematic. This is never 0 here. N is equal to 1, we get a half. N equals 2, we get 2/3, and then 3/4, 4/5, and so on. We're never going to get a 0 in the denominator. So what's the problem? The problem is that this same polynumber, r, is also equal to this polynumber. These are exactly the same polynumbers. The numerator here is obtained from this one by multiplying by 1 minus alpha. The denominator here is obtained from this one by multiplying by 1 minus alpha. Since we're multiplying by the same things top and bottom, there's no question that this object and this object are exactly the same. We've agreed that they're exactly the same polynumbers, exactly the same rational polynumbers. The associated on sequence we ought to write like this, n minus n squared over 1 minus n squared. So what is the associated sequence? Well, when we evaluate this thing when n is equal to 1, the rule is plug n equals 1 into the numerator, we get 0. Plug n into the denominator, we get 1 minus 1, another 0. We're getting 0 over 0. which is also undefined. Subsequent values are okay, 2/3, 3/4, and so on. So these two sequences agree perfectly except at the first term. There's a difference. This one was well defined, this one was not well defined. Yet we said that these were actually going to be the same rational polynumbers. So we have a problem here. The evaluation of a rational polynumber is not well defined. We were too hasty, a little bit too simple-minded in assigning a meaning to the evaluation of a rational polynumber. So we have to go back and rethink that important definition. So let's have a closer look at one of the offending examples here. These two expressions as rational polynumbers are equal. This is the example we had on the last sheet. This one just obtained from this one by multiplying the top and bottom by 1 minus alpha. Now these two expressions agree at all rational values except r equals 1. So when you take any rational value and plug it into both of these things, you're going to get the same expression unless r is equal to 1. When r is equal to 1, this will evaluate to 1 over 2, but this will evaluate to 0 over 0. And the reason is that the polynumber that we've multiplied this one by to get this, which is 1 minus alpha over 1 minus alpha, that evaluates to 1 for every rational value except r equals 1. In other words, this has the value 1 if you replace alpha with any number whatsoever. So obviously, except when you replace alpha with 1, in which case you get 0 over 0, which is undefined. So I think we can see the reason why things are going wrong. These two expressions are agreeing completely except when r just has this particular value of 1 because of the sort of artificial 0 over 0 that multiplying by this term introduced. In particular, if r is a rational number which is close to 1, but not actually equal to 1, like perhaps 0.998 or 1.0003, then we know that replacing this with r gives the same value. These things are actually equal. So the two expressions agree even for r very close to 1. It's just that exactly at 1 they happen to disagree because of the 0 over 0 that's being introduced there. Alright, so let's go back to this issue of evaluating a rational polynumber. And let's be a little bit more careful about this definition. So we'll suppose that p equals a over b, where a and b are integral polynumbers. And we'll suppose that k is an integer, or actually for sequences just a natural number will do. And the idea is we want to evaluate p at this natural number k. Okay, we're going to do two things. We're going to look at the numerator a, and we're going to write it by factoring out alpha minus k. Perhaps alpha minus k is a factor of this polynumber. This is an integral polynumber. So maybe it has alpha minus k as a factor. Maybe it has alpha minus k squared as a factor, or alpha minus k cubed. We're going to factor out as many of these alpha minus k's as we can, and write a as a product of some other sort of quotient polynumber alpha tilde, say, times this term alpha minus k to the n. And the crucial thing about this is that it does not have alpha minus k as a factor. So by Descartes' factor theorem, if it doesn't have alpha minus k as a factor, it means that when we evaluate it at k, we're not getting 0. Now it might be that this n is actually 0. So it might be that a doesn't have any factors alpha minus k. That's okay, so we include that where within the possibility that n is 0. And we do the same thing for b. We write it as some polynomial b hat times some power alpha minus k to the m, say. Where again this polynumber b hat has the property that when you evaluate it at k, you don't get 0. So here n and m are natural numbers augmented with 0. So we're including all natural numbers 1, 2, 3, and also the possibility that the exponents are 0. So this is a preliminary to defining what p of k is. So having done this, we are now in a position to define p of k. And here's the definition. And it might look a little bit surprising. There's some new things involved here, all right? First of all, there's 3 different cases, depending on the relationship between these numbers n and m. If n is bigger than m, in other words, if there's more factors of alpha minus k in the numerator than there is in the denominator, then we define p of k to be 0. If they're exactly equal, if there's the same number of alpha minus k's in the numerator and in the denominator, then we define p of k to be alpha hat of k over b hat of k. In other words, we just look at this thing over this thing. Essentially, we're canceling out the alpha minus k to the n and the alpha minus k to the n, top and bottom, because the exponents are the same in this case. And the crucial thing is these are non-zero numbers because, by assumption, this is non-zero and this is also non-zero. So this rational number actually does make sense. But there's a third case. The case when n is less than m. In other words, where there's more factors alpha minus k in the denominator than in the numerator. In that case, we are going to define p of k to be infinity. Wait a minute, what does that mean? Well, this sideways 8 is a new symbol that we're introducing. It's just a new symbol. Its name is, rather grandiosely, infinity. That's what we're going to call this sideways 8. But you can just think of it as something that we draw on the paper. It looks pretty. It's like a lemon skate. And we're going to say, we're going to agree that if this exponent is less than this exponent, then p of k is infinity. Admittedly, this is not a rational number, right? It's definitely not a rational number. It's a new expression that is outside our current number system. And it's just one of the realities of mathematics that at some point it's necessary to think about extending our number system to include a number that plays the role, or an object that plays the role of infinity. That's what we're doing now. So we're going to talk more about this. This is a very interesting development. But basically we have no choice. We have to do this if we want to have a sort of consistent understanding of the sequences generated by rational polynumbers. Okay, so this is a very important definition. Probably requires a few hours of thinking about. All right? Write out this definition, stare at it. Now let's have a look at some examples. Always the best way to understand and to start to appreciate what the definition actually means. Okay, without examples, this is all sterile. All right, so let's look at an example. Here is the polynumber p equals alpha minus alpha squared over 1 minus alpha squared. Let's think about evaluating it at the number 1. It's obviously going to be problematic because on the numerator we have 1 minus 1, which is 0, and the denominator is also 1 minus 1, which is 0. So what we have to do is we have to factor the numerator and the denominator. And we're particularly interested in factors of the form alpha minus 1. Okay, in this case it's a little bit easier if we use 1 minus alpha because the arithmetic is just a little bit easier. So I'm going to factor a 1 minus alpha out there and a 1 minus alpha out there. 1 minus alpha over 1 minus alpha, it's the same as alpha minus 1 over alpha minus 1. All right, so having done that, we see that this thing really is the same as alpha over 1 plus alpha. So 1 minus alpha appears with an exponent of 1 in the numerator and also 1 in the denominator. That's that middle case. The middle case means that we basically factor these things out. We disregard them and just consider the rest, which is alpha over 1 plus alpha, and plug 1 into that. So this is the A hat, and this is the B hat in the former notation. So we just plug alpha equals 1 here and here to get 1 over 2. And, okay, we can think about also roughly kind of a limit that if we look at this expression here, or we look at this expression here, if r is a number, a rational number that's approaching 1, then the value of this thing is going to be the same thing as the value of this thing, as long as r is not equal to 1. And then as the value approaches 1, well, this is going to approach a half. So another way of thinking about what we're doing here is we're really sort of thinking about the limit as r approaches 1 of p of r. But we haven't defined limits yet, so this is just a rather informal observation that what we're doing here is a kind of an algebraic equivalent of taking a limit, for those of you who have had some calculus before. All right, so now we're in a position to write down the on sequence for this rational poly-on sequence. The value at 1 is not 0 over 0. The value at 1 is a half, as we've just computed. The value at 2 is 2/3, and then at 3, 3/4, and then 4/5, and so on. So it gives us a completely legitimate on sequence, even though at first glance you might say this is undefined when n is equal to 1. So those of you who are used to calculus and treating functions in calculus, there's some adjustment to be made here. So we are not thinking about this thing as primarily a function. That is not what it is. It's a rational polynumber. And as a rational polynumber, this thing and this thing are exactly equal. In calculus, if you were thinking of these as functions in calculus, you would have to say that as functions these were almost equal but not quite equal because their values at 1 were not the same. We're not adopting that point of view. These are exactly the same objects for us, and so the on sequences that they generate have to be exactly the same. And so we are forced to introduce our evaluation, as we've done, to talk consistently about the on sequence associated to a rational polynumber. Let's look at another example. A bit more complicated. Here we have p equals 6 minus 5 alpha plus alpha squared over minus 16 plus 20 alpha minus 8 alpha squared plus alpha cubed. So if you set alpha equal to 1 in here, not too hard to see, you're going to get 2 over minus 3 or minus 2/3. If you plug 2 in, well, you're going to get 6 minus 10 plus 4, that's 0 on the top, and in the bottom here you're going to get minus 16 plus 20 minus 32 plus 8, which is also 0. And, well, these other values are made a little bit simpler by realizing that the polynomials that are involved here can be factored. So the numerator can be factored as alpha minus 3 times alpha minus 2, and this denominator can be factored as alpha minus 4 times alpha minus 2 squared. So that makes it clear what's going to happen when we plug in alpha equals 2. We're going to get 0 over 0 because of these terms here, at least when we have the naive approach. But now with our more sophisticated notion of evaluation, we know that that's not quite what we're going to get. To evaluate this thing at 2, what we need to do is we need to look at these factors of alpha minus 2 that are appearing in the numerator and denominator, and notice that the exponent in the denominator is bigger than the exponent in the numerator. There's more alpha minus 2's in the denominator than there is in the numerator. And that means that our definition is that P of 2 is our new symbol, infinity. How about evaluating it at 3? Well, this form of it makes it kind of obvious that the numerator is going to be 0 and the denominator is going to be non-zero, so we're going to get 0 as the quotient. And when alpha is equal to 4, or when n is equal to 4, we get a 0 in the denominator here, and no alpha minus 4 term in the numerator. So again, that's the third case. We must put in infinity. Then at 5, we're out of the woods. Then we have 5 minus 3, which is 2, times 5 minus 2, which is 3, over 5 minus 4, which is 1, times 5 minus 2, that's 3 squared. So it'll be 6 over 9, which is 2/3. So it's the associated on sequence to this polynumber is minus 2/3, and then infinity, and then 0, and then another infinity, and then 2/3, and then, well, we could evaluate some more just by substituting in here and evaluating. So we necessarily get on sequences whose entries are not just rational numbers, but also involve this new object. Maybe we shouldn't call it a number yet. It's a new expression, this sideways 8, which we're calling infinity, rather grandiosely. Probably it would be better if we called it something else, but there's no way to change the established convention with regard to this symbol. We have to call it infinity. And it's actually not such a bad idea anyway, as we'll now see by actually looking at a picture of these rational polynumbers. So we've spent a little bit of time graphing polynumbers, or polynomials. The idea with rational polynumbers is much the same, except that it's a little bit more complicated, and we have to be prepared to use rational numbers. Here's our first example of the rational polynumber alpha minus alpha squared over 1 minus alpha squared, and I'm writing it here sort of more in calculus style with an x and a y, reflecting our x and y graphs that we like to draw. So how do we come up with a plot like this? Well, it's exactly the same kind of thing that you do before. You plug in various values of x, say x equals 2. That would give us 2 minus 4, that'd be minus 2, over 1 minus 4, that'd be minus 3. So minus 2 over minus 3, that'd be 2/3. So I have to go up to the 2/3 level, and I would mark a point there. So if you calculate lots of points and then you just connect them with little lines, then you get this a graph that looks partially like this. Of course, this is just part of the picture. There's more outside, and of course we can become more and more refined. This is just my very rough drawing of this thing, not very accurate. The associated on sequence is just obtained when we restrict ourselves to the values 1, 2, 3, and 4, and so on. So the value at 1 is a half. The value at 2, 2/3. The value 3, 3/4, and so on. There's a few things to notice about this graph, of course. There's something special happening at x equals minus 1 and at x equals 1, because the denominator is 0 at both of those. The value x equals 1 turns out to be sort of an optical illusion because of the common factor of 1 minus x in the numerator and denominator. But at x equals minus 1, we have a more crucial kind of singularity. Here the graph really does kind of go further and further down as we approach minus 1 from the right. And here as we approach minus 1 from the left, it goes up and up and up and up. So it would be quite correct to say that the value of this thing at minus 1 is infinity. What about this one here? That was our second example. X minus 3 times x minus 2 over x minus 4, x minus 2 squared. Well, that's a little bit more complicated. There is now a singularity at 2 and 4 corresponding to the two factors x minus 4 and x minus 2 in the denominator. And the graph looks something like this. And this goes off to 0. So we're going to talk more about graphs of rational polynumbers like this. I don't expect you to be able to graph these so easily on your own. We'll talk a little bit more about these. These are going to play a very important role in calculus. Okay, these are very, very important objects. This is just an introduction to them. And here's the sequence that we get by looking at the values at 1, at 2, at 3, at 4, and 5, and so on. At 1, we decided we had minus 2/3. 2, we had infinity. That was our sideways 8. At 3, we have 0. You can see it going through 0 there. At 4, you can see again the infinite aspect of it. At 5, it becomes 2/3, and then it decreases from then on towards 0. So these infinities that are appearing here, of course, are very interesting. And they're reflecting the fact that the graphs of these functions are doing something interesting at these values, at 2 and 4 here and at minus 1 here. The limit of the values really is, well, it's going sort of down, 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 sort of towards minus infinity, you might say. And when we approach 2 from this side, it's going up, up, up towards plus infinity. Maybe even in some sense, the values kind of agree that maybe the infinite in this direction and the infinite in this direction somehow meet. That's what the notation is suggesting. Okay, so we've opened up a new can of worms here. We're opening up the possibility of extending our number system to include infinity. And you may know that I don't like infinite sets. Okay, and I'm very modest about things like this. So we are not proposing that we are now at the level of gods, okay, that we are now somehow superior to what we were yesterday because we've introduced this symbol. No, it's just a symbol, it's an expression that we write down on the paper which has a very specific and well-defined and coherent mathematical meaning. And next time we're going to talk a little bit more about the possible arithmetic that we might get by extending our favorite rational number system to include this new expression infinity. Is it possible? Does it work? It's a favorite subject of amateur mathematicians, so we're going to go down a little bit of that track next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.